We just discussed a problem whereby we observed that graphing of data, experimental data, is made easier in many cases when we non-dimensionalize the scaling parameters. Now we look at the extrapolation convenience when we use the non-dimensionalized parameters. So here is an example. The gravitational constant at the surface of the moon is only about 1/6 of that of the Earth. So gravity at moon is 1/6 of what we have on Earth. An astronaut on the moon throws a baseball at an initial speed of 21 meters per second at a 5-degree angle above the horizon and at 2 meters above the moon's surface. Using the dimensionless data, predict how long it takes for the baseball to fall to the ground. So, do an exact calculation and compare the result to that of part A. So, one is just a guesswork and the other one is to calculate exactly and just make the comparison. So, a simple question, and you may have done it many times, this kind of question, but here the new thing that you are involving is using non-dimensionalized data and looking at the convenience that it provides to the researchers for working out, for finding out many things. We observe that the gravitational constant on the moon, denoted by G moon, is 9.81 divided by 6, so 1/6 of what is the value of the Earth, and approximately it turns out to be 1.63 meters per second square. So gravitational pull on moon has the value 1.63 meters per second square compared to 9.81 meter per square on Earth. And the Froude number that is calculated for the value of moon, for gravitational value, we will have the velocity W is equal to 21 meters per second times sine of theta, because the baseball was thrown at an angle of 5 degrees. So if we have to calculate the vertical component of the velocity, then that will be given by W naught into sine theta, and therefore we will have W times sine theta, and theta here is 5 degrees as given in the question. When we calculate that, it has turned out that it has a value of 1.83 meters per second. This is just a imaginary photo that an astronaut is trying to throw the baseball at an angle that is given to be as 5 degrees, and they want to know how much time will it take to touch the surface of the moon. So square of the Froude number turns out to be, when we calculate it, turns out to be 1.03. And note it, because it's a dimensionless parameter, it will have no dimensions. So no units are attached to it. And this is not Froude number, this is square of the Froude number because of the under root that occurs in the denominator, and we can take the value of FR by taking square root of 1.03 whenever needed. This value of Froude number square is nearly the same as the largest value plotted. Thus, in terms of dimensionless variables, the baseball strikes the ground at t equal to 2.75. From the graph, we will see that it takes about 2.75. We cannot attach seconds to it because t star is supposed to be dimensionless. Now, converting back to the dimensional variable, we know that we used for time, the scaling variables are this. The scaling ratio is this. And therefore, when we substitute the values for t star equal to 2.75 times Z0 is 2 meter divided by the value of W0 we obtained as 1.83 meters per second. This gives us the value of 3.01 seconds. Now this is the dimensional variable time, the time. So an exact calculation, part B of the question, try to answer, is obtained by setting Z equal to 0. When the ball will touch the ground, we will have Z height equal to 0, and that will give us the value of time, and it will give us the value whatever it turns out to be, but estimated time turns out to be 3.01. And when we calculate it from the equations of motion, we see that the equation is that the answer of time is 3.05 seconds. There is hardly much difference. The estimated time turns out to be 3.01 seconds, and the exact value that we calculate is 3.05 seconds. The difference of 0.04 seconds, and if I try to calculate the percentage error, it is a very small error percentage, 0.00 something. So if the Froude number had landed between two of the trajectories that is given in the diagram, interpolation would have, since some of the numbers are precise to only two significant digits, the small difference is really negligible. That is, the small difference between 3.01 seconds, the estimated time, and the 3.05, the calculated time, is really negligible, and therefore it does not affect the result. The final result is t equal to 0 seconds. That will be treated as approximately 3 seconds to two significant digits, that is, if we ignore the decimals. So you can see the extrapolation also gives us pretty accurate result. That is the conclusion from this exercise, from this simple example, and non-dimensionalization of crucial parameters are also seen to be helpful in this process.